Inside this factory, one machine has been running nonstop for 113 years. While competitors replace their equipment 12 times, spending millions, this factory spent just $340. But here's what nobody can explain. If we could build machines that never die in 1910, why can't we do it today? November 2023, Worcester, Massachusetts. Inside a brick building that predates World War I, a single overhead shaft continues rotating at exactly 240 RPM, just as it has every working day since March 1910. Leather belts descend from this spinning shaft to power 14 engine lathes, arranged in two parallel rows across a wooden floor worn smooth by 113 years of footsteps. Sarah Mitchell, the facility's current operations manager, walks between machines that her great-grandfather once operated. Not a single lathe has been replaced since installation. No individual motors, no variable speed drives, no computerized controls. Just one central power system driving every machine through a web of belts and pulleys that engineers in 1910 called group drive, and everyone else called obsolete before it was even built. If you want to see more videos about old machines, make sure to subscribe so you never miss another video. The factory produces custom brass fittings for historic building restorations, lighthouse equipment, and museum reproductions. Modern manufacturers quote 3 weeks for custom orders. Mitchell's facility delivers in 4 days because the machines never stop running, never require software updates, and never wait for technicians to troubleshoot electronic failures. Her competitors operate CNC machines costing $180,000 each, with maintenance contracts running $12,000 annually and expected service lives of 12 years before obsolescence. Mitchell's 14 lathes cost $7,800 total in 1910, equivalent to $245,000 today, and have operated for 113 years, with maintenance costs averaging $3,200 annually for the entire system. Economics seem impossible by modern standards. A single overhead motor that hasn't been replaced since 1910. Leather belts that cost $40 each to replace every 7 years. Line shaft bearings requiring nothing but weekly oiling. No proprietary parts, no authorized service centers, no planned obsolescence. But in 1910, when the factory's founder proposed this system, every machine tool manufacturer, every industrial consultant, and every competing factory owner declared it commercial suicide. Individual motor drive was the future, they insisted. Group drive belonged in museums, not modern manufacturing facilities. The mockery was relentless. Trade publications ran satirical articles. Competitors sent salesmen to poach employees from a factory they believed would fail within months. Banks refused equipment loans, calling the group drive system industrially backwards and economically non-viable. The factory's founder, a Swedish immigrant named Henrik Bergström, ignored them all. He had calculated something his critics hadn't considered, and he was willing to stake everything on a power system that everyone else was, abandoning as fast as possible. The question isn't why this factory lasted 113 years. The question is why Henrik Bergström saw value in technology that an entire industry had already declared dead. Worcester, Massachusetts, January 1910. Henrik Bergström stood in an empty warehouse space he'd just leased for $45 monthly, sketching layouts on brown paper while his business partner, Thomas Walsh, paced nervously near the door. Individual motors are the standard now, Walsh argued, gesturing at the ceiling where Bergström planned to install overhead shafting. Every new factory in New England uses them. We'll look like we're running a museum, not a manufacturing business. Bergström, who had worked as a machinist in 3 countries before immigrating to America in 1903, spread his calculations across a packing crate. The numbers told a story that contradicted everything American industry believed about modern manufacturing. Individual motor systems required 1 motor per machine. 14 lathes meant 14 motors at $85 each, plus 14 motor starters, 14 sets of control wiring, and 14 potential failure points. Total initial cost, $1,680 just for motors and electrical infrastructure. Bergström's group drive alternative required 1 15-horsepower motor costing $340, 1 overhead line shaft system costing $520, and 14 leather belt connections at $1,800 each. Total system cost, $1,112, saving $568 on initial installation. But the real difference appeared in operating costs. Individual motors ran continuously, whether machines were cutting metal or sitting idle. Each motor drew power independently, with total electrical consumption reaching 84 kilowatts during full operation. The group drive system's single motor consumed 48 kilowatts at full load. But here was Bergstrom's crucial insight. Most machines sat idle most of the time. In a typical production day, perhaps 4 machines cut metal simultaneously while others were being set up, measured, or loaded with new workpieces. Individual motors wasted electricity running machines that weren't working. The group drive system's spinning shaft delivered power only to machines actually engaged through their belt connections. Disengaged machines consumed zero power, just mechanical potential waiting to be used. Walsh wasn't convinced. Even if your electricity calculations are correct, everyone says group drive is unreliable. One shaft failure shuts down the entire factory. Individual motors give you redundancy. Bergstrom smiled, a rare expression for the normally serious engineer. Thomas, how many moving parts in an individual motor system? 14 motors, each with armatures, field windings, brushes, bearings. Hundreds of potential failures across the system. He pointed to his line shaft diagram. One motor, one shaft, 14 simple belt connections. Which system has fewer things to break? The mathematics were irrefutable, but mathematics didn't. Matter in American manufacturing culture that worshipped speed, modernity, and the appearance of technological sophistication. Bergstrom was proposing to build a factory that would look outdated the day it opened. Boston, Massachusetts, March 1910. The New England Manufacturing Association's quarterly meeting filled the Park Plaza Hotel's conference room with factory owners and equipment suppliers, all buzzing about the Swedish immigrant who was building what they called the backwards factory. James Thornton, president of Thornton Machine Works and a respected voice in regional manufacturing, stood before the assembled group, holding a copy of Bergstrom's equipment specifications that someone had leaked from a supplier. Gentlemen, I present to you the most misguided factory design I've encountered in 30 years of this business, Thornton announced, drawing laughter from the crowd. Mr. Bergstrom has chosen to install group drive equipment that mills were replacing 20 years ago. He might as well be powering his factory with a water wheel. The criticism extended beyond simple mockery. Technical arguments against group drive seemed overwhelming to conventional thinking. The system's belt connections slipped during heavy cutting operations, causing speed variations that affected precision. Alignment of overhead shafting required skilled millwrights that were increasingly difficult to find as younger workers trained on electrical systems. Most damning was the perception of inflexibility. Individual motor systems allowed factories to rearrange equipment layouts easily, adapting to changing production requirements. Group drive locked machines into fixed positions determined by shaft locations overhead, creating what critics called permanent obsolescence built into the factory floor. Industrial consultants writing in Manufacturing Review published an analysis declaring Bergstrom's approach economically untenable in modern production environments, where adaptability and technological currency determine competitive advantage. The article became required reading in engineering schools as an example of how not to design manufacturing facilities. Suppliers refused to provide equipment financing. Standard Machine Tool Company's credit manager wrote directly to Bergstrom, "We cannot extend terms for equipment installation in a facility employing obsolete power systems. Our products deserve modern electrical infrastructure that reflects their engineering quality." Local machinists, the skilled workers Bergstrom needed to hire, were equally skeptical. William Crawford, a respected lathe operator, declined Bergstrom's job offer with frank explanation. "I've spent 15 years learning modern manufacturing methods. I won't work in a factory that looks like where my grandfather was employed. When this place fails, and it will fail, I'll have outdated experience that no reputable shop will value." Even Bergstrom's initial customers expressed concern. The purchasing agent for Worcester Valve Company visited the factory during construction, saw the overhead shafting installation, and immediately canceled a standing order for brass fittings. His explanation was blunt. We require suppliers using current manufacturing technology. Your facility suggests either financial distress or poor judgment, neither of which inspires confidence in your ability to deliver quality products reliably. By the time Bergstrom's factory began operations in April 1910, he had become an industry cautionary tale. The immigrant who didn't understand American business methods and would learn expensive lessons about ignoring expert consensus. Worcester, Massachusetts, August 1911. A summer heat wave that pushed temperatures above 95 degrees for 6 consecutive days created electrical demand that the city's power generation couldn't support. Rolling blackouts swept through industrial districts as the utility company struggled to prevent total system collapse. Bergstrom's competitor, Modern Precision Manufacturing, sat silent and dark for 4 hours each afternoon as blackouts idled their individual motor-driven equipment. Owner Robert Hastings watched helplessly as his 14 motors remained motionless, each one demanding full starting current simultaneously when power returned, often triggering circuit breakers and extending the shutdown. 3 blocks away, Bergstrom's factory continued running. His single 15-horsepower motor drew so little power during the crisis that the utility company's load reduction requirements didn't affect his facility. While competitors lost 28 hours of production that week, Bergstrom's overhead shaft never stopped spinning. The differential wasn't just operational, it was financial. Modern Precision Manufacturing had accepted rush orders expecting to complete them before the heat wave arrived. Blackouts meant missed deliveries, penalty clauses, and customers who took their business to the only factory that had continued producing, Bergstrom's backwards facility with its obsolete group drive system. September brought a different crisis that again revealed hidden advantages in outdated technology. A fire at Worcester Electrical Supply destroyed the city's largest motor repair facility. Factories using individual motor systems suddenly discovered that motor failures meant days or weeks without replacement equipment, with repairs requiring specialized electrical expertise that was now unavailable locally. Bergstrom's system used one motor, yes, but its simplicity meant that any competent machinist could perform basic maintenance. When a bearing began making noise in October, Bergstrom's machinist replaced it in 90 minutes using standard parts from the local hardware store. The factory lost no production time. By year's end, the mockery had quieted. Hastings privately admitted to his production manager, "The Swede's factory runs more consistently than ours, and I can't figure out why our modern equipment keeps failing while his primitive setup just works." The real revelation came in November, when Worcester Electric Company published annual consumption data for industrial customers. Bergstrom's facility, operating 14 lathes in a 5,000 square foot space, had consumed 4,000 kilowatt hours. Modern Precision Manufacturing, running identical equipment in comparable space, had consumed 187,000 kilowatt hours, 50% more power for the same production capacity. The electricity cost difference was $1,890 annually, enough to buy 2 complete additional lathes every year just from power savings. Multiplied over decades, Bergstrom's backwards decision represented hundreds of thousands of dollars in operating cost advantages that his critics had never calculated because they assumed modern technology was inherently superior. The industry was beginning to notice, though few were yet willing to admit that the immigrant they'd mocked might have understood something they had missed. Springfield, Massachusetts, March 1913. Thomas Whitmore, owner of Springfield Machine Company, stood in Bergstrom's factory for the 3rd time in 6 months, notebook in hand, studying the overhead shaft system he'd once ridiculed at industry meetings. "I need you to be honest with me, Henrik," Whitmore said, watching leather belts transfer power smoothly from the spinning shaft to 4 lathes, simultaneously cutting brass stock. "My maintenance costs are destroying my profit margins. I'm replacing motor brushes monthly, rewinding armatures quarterly, and losing production time to electrical failures I can't predict or prevent." Bergstrom led Whitmore to his maintenance logbook, a leather-bound record documenting every repair since 1910. 3 years of operation showed 62 line shaft oiling sessions at 15 minutes each, 4 belt replacements at 2 hours each, and 1 motor bearing change. requiring 90 minutes, total maintenance time 26 hours across 3 years. Whitmore's facility recorded maintenance time in his own logs, 340 hours in the previous year alone, servicing 14 individual motors that each demanded constant attention. His electrician's salary of $1,800 to $800 annually represented pure overhead that Bergstrom avoided entirely by using mechanical power transmission that any machinist understood. The reliability difference was equally stark. Whitmore's factory experienced unexpected shutdowns averaging twice monthly when motors failed during operation. Bergstrom's single motor had never failed unexpectedly because mechanical systems provided warning signs before failure, unusual noises, heat, vibration that allowed predictive maintenance. Word spread through New England manufacturing circles quietly at first, then with increasing momentum. Factory owners who had mocked Bergstrom began visiting Worcester, asking questions they'd once considered beneath them. How did belt tension affect power transmission efficiency? What maintenance schedule kept line shafts running indefinitely? Could group drive systems really eliminate electrical maintenance costs almost entirely? By 1915, 6 factories in Massachusetts had converted from individual motor drive to group drive systems, explicitly citing Bergstrom's operation as proof that older technology could outperform newer equipment when properly implemented. The conversions required substantial capital investment, removing individual motors and installing overhead shafting, but owners calculated payback periods of 3 to 5 years through reduced maintenance costs and lower electrical consumption. Industrial publications that had published scathing critiques in 1910 now ran technical articles explaining group drive advantages. Machinery Magazine's 1916 feature titled Reconsidering Mechanical Power Transmission opened with frank admission, "Recent industrial experience suggests that our profession may have abandoned group drive systems prematurely, mistaking technological novelty for engineering superiority." Bergstrom never gloated, never reminded critics of their earlier mockery. When visitors asked why he'd chosen group drive despite industry opposition, his answer remained consistent. "I calculated the numbers. The mathematics didn't care about fashion or what people called modern. Physics doesn't change because we prefer different technology." The validation was complete, but the real test of Bergstrom's engineering philosophy would come not in years, but in decades, as his obsolete factory continued operating long after modern facilities had replaced their equipment multiple times. Worcester, Massachusetts, 1950. Henrik Bergstrom, now 81 years old, walked through the factory he'd built 40 years earlier with his grandson Robert, showing him the same overhead shaft that had been spinning since 1910. "Every factory that mocked this system has replaced their equipment at least twice," Bergstrom explained, his hand resting on a lathe that had never been rebuilt. "Some 3 times. They paid for modernity with constant replacement costs." The post-war industrial boom had created unprecedented demand for manufacturing equipment. Factories across America were installing their 3rd or 4th generation of machine tools, each generation promising improvements over predecessors but requiring complete replacement when newer technology emerged. Bergstrom's facility operated the original 14 lathes from 1910, each machine still capable of holding tolerances within 0.002 of an inch. The overhead shaft had required 1 replacement in 1934 after a delivery truck struck the building and damaged the bearing support, but the motor itself had never been replaced, just serviced with new bearings and fresh windings. The mathematics of longevity were extraordinary. Competitors had spent and sold average of $8,400 per decade on equipment replacement and upgrades. Bergstrom had spent $340 in 40 years, basically the cost of his original motor plus routine maintenance. The compound savings exceeded $33,000, enough capital to have built 3 additional factories of similar size. Reliability proved equally valuable. During World War II, when manufacturers struggled to obtain replacement parts and skilled electricians for military service, Bergstrom's mechanical system continued running with minimal intervention. The facility produced brass components for military equipment throughout the war without a single day lost to equipment failure. Younger engineers touring the factory expressed disbelief. "This is the original installation from 1910? they would ask, examining leather belts and cast-iron pulleys. It still runs production work? The questions reflected how completely American manufacturing had forgotten that equipment could be built to last indefinitely. By 1960, Bergstrom's factory had become an industrial anomaly, the only facility in New England still operating group drive equipment. Manufacturing consultants recommended conversion to individual motors, arguing that replacement parts for line shafting were becoming difficult to source. But Robert Bergstrom, who had taken over operations after his grandfather's death in 1955, ran the calculations just as Henrik had taught him. Converting to individual motors would cost $18,000 for equipment plus installation. The current system costs $280 annually in maintenance. Why spend $18,000 to achieve what we already have? Robert asked consultants who couldn't provide convincing answers. The factory continued running, decade after decade, becoming a living museum of industrial engineering principles that modern manufacturing had abandoned, not through sentiment or stubbornness, but through simple mathematics that proved longevity was more economical than constant replacement, regardless of what industry trends suggested. Worcester, Massachusetts, present day. Engineering students from MIT visit Bergstrom's factory as part of a course on sustainable manufacturing, photographing overhead shafting that has operated for 113 years, while their professors explain concepts that modern industry has completely forgotten. The factory represents a timeline of industrial philosophy compressed into one building. In 1910, when factories were installing individual motors as fast as possible, Bergstrom installed group drive and was mocked. By 1950, those modern factories had replaced their equipment 3 times, while Bergstrom's original installation continued running. By 1990, they had replaced equipment 7 times. By 2023, 12 complete equipment generations have come and gone in competing facilities. Sarah Mitchell, Henrik Bergstrom's great-granddaughter and current operations manager, maintains the same maintenance logbook her great-grandfather started in 1910. The leather cover is worn smooth, the pages yellowed, but the entries tell a story that modern manufacturing has forgotten how to write. Continuous operation without replacement, repair without obsolescence, longevity without compromise. Every maintenance textbook teaches planned replacement cycles. Mitchell explains to the students gathered around a lathe that was already old when their great-grandparents were born. Change equipment every 15 years. Budget for technology upgrades. Accept that manufacturing assets depreciate towards zero value. My great-grandfather proved that equipment doesn't have to fail if it's designed properly and maintained consistently. The economic comparison staggers contemporary understanding. A modern CNC lathe costs $180,000, requires $12,000 annual maintenance, and becomes obsolete within 12 years. Over 113 years, replacing that equipment cycle would cost approximately $1.8 million per machine position. Bergstrom's 14 original lathes cost $700–800 in 1910 and have incurred roughly $42,000 in maintenance costs across 113 years. The difference isn't technology, it's philosophy. Bergstrom designed for permanence in an industry that was already embracing disposability. He chose simplicity when complexity seemed sophisticated. He valued reliability over features, longevity over novelty, and mathematics over fashion. Modern manufacturing has lost this capability almost entirely. Engineers no longer design equipment expected to outlast their careers. Accountants don't calculate century-scale ownership costs. Manufacturers don't build machines assuming indefinite operation. Planned obsolescence isn't a conspiracy, it's the fundamental assumption underlying contemporary industrial design. The overhead shaft in Worcester continues spinning at 240 RPM, powered by a motor that predates World War I, driving lathes that have machined millions of parts across 11 decades. It proves that longevity was possible, that equipment could be built to serve multiple generations, and that the obsolete technology an entire industry abandoned actually embodied engineering principles more sophisticated than what replaced it. The factory Henrik Bergstrom built isn't just running after 113 years. It's asking a question that modern manufacturing cannot comfortably answer. If we could build machines to last forever in 1910, why did we choose to stop?